gram Kelvin, it takes the least amount of joules to raise 1 gram a certain 1 degree Kelvin.
Okay, so it's going to take the least amount of heat to cause a temperature change. So it takes, it takes 0.13 joules to increase its temperature by 1 degree, or 1 Kelvin, and everything else takes more. Okay, so you see how metals are really, really low in specific heat capacity. That means they increase their temperature very quickly, and then they decrease their temperature very quickly. That means that they're very inefficient at retaining heat. But who's just great at retaining heat? Water, okay, and that's what we use water for a lot of things for that reason. Okay, so we did that. We did, back the other way. We didn't talk about this in depth, but I do want you to know that the specific heat capacity being different units in heat capacity means that one is an extrinsic property, meaning it does depend on the amount. That was the big C, that was the capital C heat capacity. It depends on like how big your coffee cup is versus how small. Like it'll absorb more heat if it's bigger, it'll absorb less heat if it's lesser. And then specific heat capacity is an intrinsic property, means it's an inherent property about a compound, and so that number doesn't change. It is a standard number. But there is a different number for every substance in the world and every state of that substance. So water, we say water, but we actually mean water liquid, is 4.18 joules per gram degree C. And these others, they will always be given to you, but you need to write them down because I don't want you to not use them in their appropriate spots in today's problems that we're going to be in. So ice and vapor have two different heat capacity or specific heat capacities versus that of just liquid water. Know that those will be used in their specific instances on a heat curve. And whenever we're dealing with calorimetry problems or heat exchange problems, by the way, is heat a thing? Can you measure heat? No. Okay, so heat is not a thing. You can't measure heat. You can only measure what? Temperature, and then the change of temperature, right? And then you can indirectly calculate heat. So heat is a transfer. It's not a thing. It is a transfer between two objects of different energy. And so when we talk about calculating, we do generally use these measurements of Q equals MCAT, and occasionally we talk about talk about heat as enthalpy. So Q as enthalpy. It's not exactly Q equals delta H. That is not exactly correct. It depends if we're talking about 1 mole of it or not. So delta H's units are, the way you achieve delta H is Q divided by moles. So if we're talking about like 1 mole of a substance, then Q does equal delta H. But if we're not, we always have to divide by a quantity related to its amount, which is moles. So delta H is enthalpy, and enthalpy describes heat or heat transfer. But it is adjusted by per mole of that substance. So just note that we'll talk about this a little bit more today as well, but we have to find Q to get delta H. All right, so in terms of information for today, let's talk about heat curves first and then we'll move on. So, before I get there. So this is a heat curve, and I know it's not a curve, but that's what we have to call it. And in a heat curve, it's supposed to track the state changes over time as heat is added. Well, as heat is added, generally, we all say, oh, heat's added, what should happen to temperature? It should increase, as you can see here, and you must know these axes, okay? I'm not going to always tell you the axes. If I have you draw your own, you need to have it drawn appropriately. Throughout this change right here, there is a temperature change. But throughout this change here, there is not a temperature change. So there's a difference in what heat is doing in each of these instances. So what you should know first is that these vertical, or these slants here, the slants are considered heat changing in temperature, right? But that's just it. There's no phase change whenever the heat or the temperature is rising. It is simply the molecules are getting, they're moving faster, but they have already phase changed. So in this instance, let's call this ice. Let's call this negative 20 degrees Celsius or something down here. And let's call this 0. Let's call that 0 degrees Celsius. So during this change here, this ice crystal, let's say it's a big block like this, okay? It is simply taking its crystalline structure and it's starting to move some. Okay, as it starts to move some, it starts to vibrate more. It's actually increasing in energy, but not kinetic energy, not translational kinetic energy. which is the energy that, it is increasing translational conducting because that is what the temperature is relaying. So temperature, which I think I typed, oh, let me show you this first, because this was what I sent you guys yesterday. Did you guys see this on Sally yesterday? Sally? I sent this on Sally? Okay. This I thought did a really clear, described very clearly the differences between phase changes and temperature changes. So key idea is that temperature does not measure the entire internal energy component, only the translational and kinetic energy, because we know that temperature is directly related to kinetic energy average. And that translational energy is just energy of motion, right? Moving things, translating things left and right. So that's happening not during phase change. That's when the temperature is rising. But during a phase change, your potential energy is what's changing. So if I have a ice crystal and they're very close together, they're very stable. They are very, very stable together. But as I turn and melt them, the particles start to separate. Well, this stability means it has low potential energy because it's very stable. Remember, positional energy is what potential energy is referring to. And as they melt, what happens? What increases? Potential energy increases. So as that potential energy increases, it's that position that they're like moving away from each other. You're overcoming, right, this part down. This is like a phrase you'll hear all the time. You're overcoming intermolecular forces between those particles. Well, if this is ice, this is water. What intermolecular forces at play here? Hydrogen bonding. And there's also some little bits of dipole and Lorentz dispersion, because actually Lorentz dispersion is in everything at all times. But if you're overcoming intermolecular forces, doesn't that take energy? Yay or nay? Yes, it takes energy to move them apart. But if it takes the energy and it uses it as this potential energy is changing, because you're using the heat energy to do something, you're doing work, the temperature doesn't increase because it's no longer there. The temperature doesn't increase because it's not like they have more kinetic energy only. The energy of heat has been utilized for this purpose. Well, once it gets to the point where the potential energy is increased, you've utilized that heat energy to do that potential energy change, then it's like, okay guys, I'm to the point where I can't be a liquid anymore, right? Because it just melted and it can't be a liquid anymore. It's going to start to eventually want to change to gas, but it's going to take so much energy to pull this apart even more, and even more. That's at the point that it's going to turn to gas, it's going to be a much higher temperature. And so that's when it phase changes again. So, that's when it will phase change again. So I'm going to kind of relate these terms to our graph that we have here. So here, temperature is changing, right? So the change in temperature is related to a kinetic energy change. But here, temperature is not changing. What energy is changing here? Say again? Potential energy, right? So at here, temperature is changing, so kinetic energy is changing. Here, potential energy is changing. Here, kinetic energy is changing. Oops, temperature is changing, so kinetic energy is changing. Just remember that kinetic energy is related to temperature change. And so what phase change is happening at let's label these 1, 2, 3, 4, 5. What phase change is occurring at 2 right here? Melting, right? So we're going from solid to liquid, so that's melting. What's another word for melting? Fusion, right? So this is actually signified by a particular enthalpy value as delta H fusion. Fusion means melting. And then as we go from solid and this potential energy is being overcome, it's going from its solid state kind of morphing into like a more fluid state, which would then eventually be liquid. We've turned liquid. Now the liquid has heated up so much, it's like, man, we can't be a liquid anymore. We're going to have to poof into vapors, right? So this is definitely a evaporation phase change or vaporization phase change. And that delta H, that enthalpy, is called delta H DAP, or vaporization, right? And then after it has become vaporized, it is a gas, and the gas continues to heat up, but there's no phase change after that. It's just a hot gas versus a cold gas. So who's ever put their hand over steam? That is hot. Who's ever put their hand in warm water? Not as hot, right? And so that state change does contain more energy, which would then correlate with more kinetic energy, which would increase the temperature, which is why steam can burn you, but water necessarily won't burn you. Okay, so that's kind of our flow here. So what we can say is, if there is a temperature change, I'm on a different color, sorry. If there is a temperature change, can I calculate the heat associated with that temperature change? Yay or nay? I see heads shaking yes. What's the formula for that? Temperature and heat. We have an equation. Q equals MCAT. Okay. Q equals MCAT. Now, this C is going to be referring to what state of matter? Solid. Okay, so I'm going to put CS right there. I'm going to call this Q1. Okay. Second stage, let's skip 2 for a second. Let's go to the third stage, actually. This one has a temperature change, so you're going to do Q2 is equal to MCAT, but for what state of matter? Liquid, and I'm going to call that Q2. And then another phase change, and then gaseous phase, the temperature is still increasing. We're going to say Q3 is equal to MCAT, but what is our C value for whatever the vapor is, the gases? So we have 3 separate Qs for calculating if we go all the way from a solid state all the way to a gas phase. But wait, there's more. This energy associated with phase change has its own Q associated with it. Same thing here. So I just told you that delta H is calculated by doing Q over moles, right? So how would I find Q if I know both of these? So delta H times mole, or the number of moles you have, would equal Q. This is Q of phase change. So what values would you need for this? For this one. I would need to know the enthalpy of that phase change. I would need to know what I just wrote here. What's the value for enthalpy of fusion? What's the value for enthalpy of vaporization? Those actually have numbers, and I just skipped them for a minute because I wanted to show you this part first. So these are the ones we'll utilize probably most frequently. Delta H vac, delta H fuzz, and delta H of solution. When these are not chemical reactions, right? These are all phase changes? Yes? So these actually have values and that they are dependent upon the compound you're talking about, but I will tell you the delta H vac of water is 40.6, probably 40.1, I'll be mixing my numbers, but it's 40-ish kilojoules per mole, and delta H of fusion is 6.01 kilojoules per mole. I'm doing this from memory. I might have to go back and check my values in a second. You know, I knew I prepared for this. That's a 7, and that's a 2. I like how I don't even look. I'm just like going with it. Okay, so these values obviously are very different, right? And somebody can maybe postulate why delta H vac is so much bigger than delta H fuzz. What is this energy doing? Come on, Vicky. Okay, so we're taking this one from liquid to gas, and this one from... Okay, so why are they different? Why would it require more energy? What's the energy doing? Okay, so they are adding more potential energy, but there's something I said earlier that I wanted to make sure we repeat. Yeah. Okay, and I use that word break very loosely. I swear on the AP exam, if you say break intermolecular forces or break bonds when you're not supposed to, they think that, oh, they have a big misconception. They think we're breaking things, but really we're overcoming. Use the word overcome. It'll save you points. Overcome IMFs. And this one has a lot more to do because that liquid phase has to overcome every hydrogen bond, every single one, so it can separate into gases. Whereas going from solid to liquid, there's just a couple of hydrogen bonds they have to kind of overcome because not all of them are overcome, because if they're all overcome, then you have turned to gas already. But you just have to loosen them up some so they can start to move into liquid phase. Does that make sense? But quantities are different here. Yeah.
Is it specific to you?
Not for this one in particular, because simply we are not utilizing that for our calculation. But it does have something to do with the size of the number, and like overall for water is very large.
Yeah, it's confusing because it like takes a lot more energy to convert it to a liquid than to a gas.
Not for water. For a liquid, it only takes from solid to liquid 6 kilojoules, and from gas it's 40.
Oh, okay.
Sorry, yeah, I listed vape first and then fusion second. FYI. Okay, so H solution is going to be when I'm taking a powder and I'm putting it into aqueous solution to make a solution. And I won't give you a specific value for that, but I will say there are some solution processes that You could make a hot pack with, or a hot hands kind of thing. You guys ever seen the ones with sodium acetate in it and you break it, it makes it warm? So that's just sodium acetate and water separately, and you put them together and you make a solution, and then how does it feel to you? It feels warm to you. Okay, so where's the system at? You or the pack? The pack. Is the pack losing energy or gaining energy? Losing energy. It's putting it out to the world, right? So is that X or endo? All right, so delta H would be negative. And if separately, if you felt that cold pack, who's ever had an ice pack or cold pack, okay, you've had an injury, you put something on your leg or something, then to you it feels cold, because what's it doing to you? Stealing your energy, and it's like it's going to just cause that heat transfer from you to it. And so it is taking energy in, so it is endothermic. So these are going to be either one based on the situation at hand. These in this case are definitely energy that's going into that vaporization or into that fusion. But if I reverse this and did, what's the opposite of vaporization? Condensation. Okay, so delta H of condensation, would that be opposite? I mean, that would be a negative value. The same number applies though. And then delta H of, what's the opposite of fusion? Say it again? Solidification, maybe? Or no, sorry, fusion is melting, freezing is the opposite, right? Sorry, I thought I heard somebody say freeze. Okay, so delta H of freezing would be a negative value of 6.02. It's the same number, it's just opposite signs. It's the same process, yeah. It actually might be them to add together. Generally, it's published as its own little entity called sublimation or deposition, but it's probably just the summation of those. I don't have the number off my top of my head. Yeah.
Does the delta H of the solution have a value?
It does. Like, different things release different amounts of energy. So this is all talking about water. So this is only for water. Every compound has a different one, different numbers. And so solutions, it depends on what I'm dissolving. It'll have different numbers throughout as well. All right. So let's do 5 and 6. Let's do 5 and 6 together. I'm going to start with the big boy, number, whatever this is, 5. You have this on your paper, right, for heat transfer? Okay, we're going to track on how to do this one time, and then I'm done. So please write down and participate through calculations with me so I don't have to calculate, because I'm going to be writing. So question, how much heat, that means Q, is required to change mass 52.9 grams of ice to steam? Uh-oh, you have to go through the whole shebang, right? Q 1, 2, 3, 4, and 5. 5 Qs here. Every step has its own Q. And ice from negative 15 degrees Celsius to steam at 230 degrees Celsius. Okay, so our first Q is this right here. Is that a phase change, yeah or nay? No, so that's not a phase change, that's just ice heating up. So if ice is heating up, that is heating up, meaning the temperature is changing, so what equation do I use? MCAT. So Q1 is, I'm just going to put this one right there, is mass, 52.9 grams. What's the specific heat at this instance? 2 point what? Say it one more time. 1, thank you. Joules per gram degree C. And what's my temperature change? So 0 is where ice starts to melt, right? Negative 15, so what's final minus initial? Just 15 degrees C, and then someone will calculate that for me. Somebody at this table, Alvin's group. Q2, that's going to be this right here. Is that a phase change, yes or no? Yes. Is energy going into cause temperature change? What is that? 1,600.35 joules. Okay. No rounding yet. This is not the end. Okay, so is energy going into temperature change, yay or nay? Nay. What's it going to do? Overcome intermolecular forces and cause potential energy change. Okay, so that right there is going to be what equation? Mole times delta H. And right, we have our delta H's on our paper. I don't know what 52.9 divided by 18. I'm going to show my work like I show my work. You guys just like to divide. I like to show the conversion to 1 mole of water is 2 grams. Okay, so that's grams to moles. And then what's the delta H buzz? Because this is fusion, right? 6.02 kilojoules per mole. So I already know them. I'm going to have to choose kilojoules or joules. Anybody got that for me? kilojoules. Okay. Q3. Now we're going from 0 to what? When will water start to phase change again? 100. So this is common knowledge. You know that it's going to start to boil at 100. So then our mass, 52.9 grams. What's my specific heat capacity of water, liquid? 4.18 joules per gram degree C. What's my delta T? It is, or 100 minus 0 is 100. And that, somebody can calculate for me in a second. Q4 is referring to what? Another phase change. So we're here now. This is delta H that. Okay? What's that value? 112.2 joules, right? Okay. And then this again is whatever this mole is. Did anybody calculate that? Can you just tell me the moles here? 2.93. Thanks, Alvin. And that's moles. And then what's my delta H for vaporization? 40.7 kilojoules per mole. Okay, so moles cancel. Got kilojoules. Anybody? Thank you, human calculators. I need you. 119.25 kilojoules. Okay. And then lastly, we're heating this baby up to this 52 grams up to 230. So from 100 to 230, difference in temperature is 130. What's the specific heat capacity of steam? What was it? 1.99. I don't memorize these in particular. I don't use them too often. And then what's that value when you multiply? 2 joules. Okay, last step would be what? After they're in joules or kilojoules, right? Choose joules or choose kilojoules, add them up, and that will be our final heat required to get from step A to step Z. Okay? So it's a lot. It is, but not every question will have you go all the way from ice to steam. It might stop you halfway and go to liquid, or stop you halfway and go to partially through liquid, so like 50 degrees Celsius, not 100. So, but that should support you in everything after this. Question? Adding, do you have an answer?
Yeah, 175
Kilojoules, 175? 175-ish kilojoules? 13. Okay, that sounds reasonable. Okay, so in this case, a lot of energy it takes to just boil some water, 20 or 50 grams of water. Okay, so in terms of if this were a cool curve, I know this is a cool curve, guys, because it's not really a curve. But if this were a cooling curve, what would be the only thing that's different? Okay, it would be upside down, but what else? Negative, because all of that was heating up, so endothermic, right? This is all endo all the way, because you're going increasing in energy. But if you had a cool curve, hold up, cool curve, then everything would be opposite in sign, everything would be exo, and exothermic throughout be a negative delta H, I mean a negative Q at the end. Does that make sense? Yes, yes? Okay, well, I covered a lot of information there about phase changes. I had a whole worksheet on it, but I felt like I could do it justice in half the time. So I tried that to see how you guys do. Take a breather for a minute, and then we're going to do this example problem because this was on your problem set as well. And this is going to be supporting this for our lab as we get to it in just about 5 minutes. Please write down your givens for this. Or actually, before I move on, who felt like pretty good about finding this information on their own? This was number 3. I think it was 3. Was it 3 on your problem set? Yeah. Okay. Who felt good about this? Yeah, go for it. Give me the setup.
Okay, so I converted the moles. 130 grams per mole.
Okay. This is what? I'm sorry. This is 1 mole is 52 grams.
Yeah, I got like
0.538 moles. Okay, so we did that. Next.
And then I was trying to define Q,
Okay, what did you call Q? I know this is what I want everybody to do for me throughout this whole unit. Q of what? We're talking about Q the calorimeter or Q the combustion? You want to talk about Q the combustion? Okay, to verify that, it would be very difficult because I don't have I don't have a specific, I don't have a heat capacity for combustion because the heat capacity is referring to what? The calorimeter, right? Okay, so here's what you do. Who's the system here? The combustion reaction or the calorimeter? I heard a mixture. Kirk, what did you say? Because that's the thing reacting, right? That's our system of interest. We're looking to see its information, like in terms of its heat released. So this is the system, but who's my surroundings? The calorimeter. It's capturing that energy and it's measuring it and kind of backwards track back to the combustion. So Q is the combustion, and as you can tell, is it endo or exothermic? It's raising the calorimeter's temperature from 25 to 142. So it's releasing its energy to the calorimeter, right? Itself is then exothermic. You really got to wrap your head around system and surroundings, and you have to talk to yourself. I talk to myself on this. Like, the system has released energy to the outside. The system is exothermic. The system has a negative Q. Okay? That negative Q is captured by the calorimeter. So the calorimeter gets the positive because it's absorbing that energy, right? Okay, so who cares about a combustion reaction? I don't really know a whole lot of information about that. All I know is this moles. That's it. But I do know so much information with the calorimeter. I can find the Q, the calorimeter is set equal to negative Q, the combustion. Got me? All right, so Vicky, pick up from there.
All right, so this is the mass for the non-calorie, compared to the joules, the specific heat for calories.
Okay, so you went ahead and did that first.
Right.
Okay, I'll stick with that first. What did you, you took this to calories?
Yes.
Okay, so 2.60 joules per degree Celsius. Converted to calories, what's that conversion?
1 calorie over 4.
Joules, okay. So that joule has canceled.
And then I multiplied that by the temperature difference.
117, right? So the temperature difference, T final minus T initial, is a positive temperature change of 117. And then we got our Q of the calorimeter to be what? 1.6. 126, thank you. I did joules first and I converted 126.46 calories. So this is the number of calories the calorimeter absorbs. So how much did the combustion release? That, right? Exactly that. So it released this much. So the Q combustion is negative 126.46 calories. Okay. You with me, guys? All right, so then how do you find the heat of combustion, the delta H of combustion?
I divided the calories by moles.
Okay, so delta H, and this is just happens to be of a combustion reaction, is going to take, just like I had over here, if you did not write this down, this is your best friend probably for the next 2 weeks. Delta H, how do you get it? You take Q divided by moles. And since we have moles, we had negative 126.4 calories divided by moles that we got at first, 0.538 moles. And what's that value? Negative what? I got, yeah, negative 135 calories per mole. Anybody else? What's up? Is there an error? Because I did mine all in joules, so this is 72 calories. All right, it's okay. I tend to do this too. So this is 72. Yes, yes? Okay, 72 calories, negative 72 calories. I couldn't fact check because I did everything in joules. So regardless though, once you get your Q divided by your moles, you should still get negative 135 calories per mole. Okay, and do me a favor. Oops, you got a wireless switch. We'll run to the phone every time. All right, so we are going to walk through our lab now. Sense here, as I'm videoing up again for Chloe. Okay, so my 2 cents is, first off, you know the Enormer Challenge has begun. Okay, the challenge has begun. You have a specific set of instructions that are here, the criteria that must apply. It has to be safe, environmentally friendly, inexpensive. So you're going to be looking at aspects of that, looking at MSDS sheets for each of your chemicals that you are assigned, because you're going to only be assigned four. And you also have to, it can't be huge, like we can't be carrying a barrel in a book bag with the hand warmer. It's going to be small, like 50 milliliters maximum. It costs as little being green. And so I got to show you guys that too. With your lab sheet, you see that there is a pre-lab associated with this, but if you don't do the pre-lab right now with your group, you can do it tonight. You can even do it a little bit tomorrow, but this is going to be like really important for the background knowledge about breaking bonds, forming bonds, how is energy created through a reaction, how is it absorbed. So like the stuff with entropy, with disorder, you had a little background reading on it when you did your first reading of the study of it in SMI, but there's a lot more here, and I want to be able to talk to you about this tomorrow. So if you don't do all this right now, I understand. The research components about how to design, what are the health risks, what are the environmental risks, they're going to be here as well. So in terms of what we're going to do right now, you saw it's 5 grams of magnesium sulfate anhydrous. You're going to be rehydrating it. That's actually what you're doing. When you rehydrate it, there's a temperature change associated with that. So you're measuring your temperature change, and then you're going to backtrack and calculate the heat capacity of your styrofoam cup. But you're learning how to use your equipment, so you're like, tomorrow's not like your first day. You're trying to figure out the intricate details of your equipment. And then after that, you're going to do hot water and cold water, 50 milliliters each, put together. It should come to the average of those 2 water temperatures. That is not noted in your lab. If you start with a 50-degree water temperature and a 30, what should be the intermediate? 40. It should be 40. If it doesn't reach 40, where's the energy going? To the coffee cup calorimeter. It could be escaping, because our coffee cup calorimeters are pretty cheap. But we're assuming, I can't account for it escaping really, but I can assume that it's going to the coffee cup. And that's what our big C will be. We'll calculate what that is based on the temperature change that did occur. That big C heat capacity will be calculated. You will use the exact same coffee cup tomorrow. We'll label it like 1, 2, 3, 5, so that you already have that standardized. That's calibrated. Got it? All right. And then so before I can take up more of your time here, I did not show you this. You guys remember voting for Teaching Titan last year? Teaching Titans, where you voted for a teacher that it was based on the characteristic of the month. So what I want you guys to do is during whenever you're getting your groups, you're going to go here and vote here. There's a committee of teachers that are trying to help with teacher morale and celebrating teachers, and it's based on student responses. So I'm not voting, you're voting. And as this, you can see the link will stay there for you. But I'm going to scroll down first to show you your groups. So I did a randomized little randomizer. You can see your groups for this unit. And I'm going to try to randomize them, because you guys like to pick the same people, but you're going to be with each other for a year. You should know everybody's names. You should know something about everybody. Maybe you can make a new friend. You have to be friendly to make new friends, though, okay? I'll help you guys with your social skills. But let's go ahead and get in those lab groups. Grab a laptop, and then I'm going to show you rotating in the back. We're going to learn the ropes here. Learn the ropes. So the middle station's mine. If you guys could go to the outside lab stations, the back middle one is mine. I'll show you. I have equipment back there. Goggles and shoes. Goggles and shoes. Chloe, where's Chloe at? Okay. Arshia, Lucas, and Allie. Just make sure that when you include your doc, you're gonna get Chloe there. So we have about 35 minutes, guys. So let's go ahead and get our lab groups. Oh yes. Okay, lab groups. I hope that you go down the lab groups while you're at home. That means you find stuff out of the way. Send a material manager from your group come see me.